Yes, I am serious. Or maybe today I should say that I'm serious because we'll be working out 100 series. We'll see if they converge or they diverge. And of course, we'll be doing this in one take. But I don't know how long this will take me. As you guys can see, we have the clock over there already. Take a guess, how did I put down the clock on the board? But anyway, this right here, it's good for Calc 2. And as you guys can see, I have the file right here already. And you guys can, of course, go download the file. The link is in the description for you guys. And I spent so much time selecting all these questions. So if you guys like this video, please give me a like. Thank you guys so much. And if you guys find this video to be helpful, you guys can subscribe. You guys can expect more of this kind of video in the future. But I don't know how many more, but I'll do like my regular videos too as well. But anyway, best luck to all the Calculus 2 students, right? Especially if you have to take your Calculus 2 final exam soon. And also for my student this semester, don't worry, I'm not going to put 100 questions on the final exam. Maybe just like 25, not just kidding, I don't know. But anyway, best of luck to you guys. And I just want to say the special thanks to the following right here. First of all, if you guys have seen my 100 integral video, then you guys know about Loss. He was battling and he's still battling with his cancer. But let me tell you, he's actually almost done with all of his treatments, so that's a good news. And Loss, thank you so much for all the conversation that we had, and thank you for all the support that you have given me and Dr. Payam. Thank you. You're awesome, and keep fighting. And Chester, you're awesome. Let me tell you guys about Chester. He actually has to go to military duty soon, and I just want to wish him the best luck. And it's so cool to talk to you, and after I talk to you, I feel so much better. Thank you for the support, and you are such an awesome individual. Thank you for the service for the country, and best of luck to you for your journey. Yeah. Dr. Payam, make sure you guys subscribe to Dr. Payam, a good friend of mine. He also did a 111 linear algebra true-false question video. So if you guys haven't seen that, go check that out. I will have the link in the description for you guys. And of course, I want to say thank you to all my subscribers, all my supporters. Thank you guys so much. Thank you, seriously. Thank you to all my Patreons. Thank you. Like, seriously, it's so much fun to do videos, especially now I know I have so many subscribers. It's just amazing. Thank you. And of course, my girlfriend, Jia. And hopefully, I can finish this video in 6 hours, and I will go see you later, alright? Anyway. Okay, special shout out to Johnny and Mr. Autumn from King James School in UK. I think this right here has nothing to do with LeBron James, but I don't know if there's anything to do with LeBron James, then let me know, right? Last time, actually, I want to give you guys a shout out already, but I wasn't satisfied with the math in that video, so I made that video private. But now this is a shout out. Thank you so much for your support, and then hopefully the people who are watching this from King James School, you guys can be happy and leave a comment down below and let me know. And of course, I want to wish everybody to have a happy life. Yeah. Okay, before we start, we have some house business. First of all, let me tell you guys the top 4 secret when you are doing the convergence or divergence for a series. Let me introduce you guys, if you don't know this already, the fact. Namely, we have the limit as n goes to infinity of 1 plus a over n raised to the bn power. This right here is just e to the ab power. So all you have to do is pay attention to if you have 1 and then one number, this is right here, and then bn and then n and n, they have to match, and n goes to infinity. And later on, if necessary, I will just be quoting this fact right here, and I'll just tell you guys the fact. I'm not going to go through the computation. Next, we have the list. In another word, this right here, it's actually just like a comparison of the kind of infinities that we'll be dealing with. So, for n goes to infinity, ln n is the smallest kind of infinity, and next, it's a power function when we have n to the p's power, and in this case, p has to be greater than 0. Next, we have b as the base raised to the nth power. B has to be greater than 1, so this is like the exponential part. And then we have the factorial, the n factorial right here, and then the biggest kind of infinity that we'll be dealing with is n to the nth power. Because as you can see, the base is infinity, the power is also infinity. That's pretty crazy. And you know, the idea of the list is that this right here is so small, if you put ln n on the top over, let's say, n to the first power, this right here will actually go to 0 as n goes to infinity. So I'm just going to quote the list whenever we have to do this kind of comparison. So we are going to keep this in mind. And I will also have to tell you, this is the special one. It's not on the handout, so you have to really watch the video in order to know what I'm going to tell you, right? Note, this right here, it's a really, really common one. ln n is less than square root of n, right? This is true for all n value, n greater than 1, greater or equal to 1. And later on, you will be using this. We'll be using this a lot. So keep this in mind. Next, the limit as theta goes to 0, sine theta over theta is equal to 1. Here is the deal. Please do not say take the derivative on the top, take the derivative on the bottom, because in order for you guys to know the derivative of sine theta, you actually have to know this limit first. Therefore, you have to do geometry to figure out this limit before you can talk about derivative. So please do not say use L'Hopital's rule for this limit. Lastly, of course, not least, how can we forget about our best friend on my shirt right now, right? 1 over 1 minus x is the sum as n goes from 0 to infinity, x to the nth power. This is true if the absolute value of x is less than 1. This is, of course, the geometry series. And we have other friends right here as well. But anyway, I will show you guys this along the way. Okay, so that pretty much is it. I was going to say hopefully you guys all like this video, but we are about to get started. Okay, 7-minute intro. Okay. Here we go. We can do this. Okay, first of all, the sum as n goes from 1 to infinity of 1 over n. This right here, as you guys all know, this is the p series or the harmonic series. P is equal to 1 right here. So this right here diverges. But I want to show you guys the classic proof of this first. So let me just tell you guys why this right here diverges for the first one. So here we go. For the sum right here, of course, you're plugging n equal to 1 right here. And of course, n are just the positive whole numbers starting from 1 and all that. So we have 1 over 1. And then next, we plug in 2. So we have 1 over 2. And then 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7, and then 1 over 8. And then dot, dot, dot. You just keep adding this up forever, right? And now, this is how the proof goes. As we can see right here, this right here is actually going to be bigger than the following. 1 is still 1. Right? So that's okay. And then 1 over 2 is still 1 over 2. But 1/3 is actually bigger than 1 over 4 if you just make this comparison. So I'm just going to write this down right here for you guys. And because now I put this down, this expression is actually bigger than this expression. Because as you can see, 1/3 is bigger than 1 over 4. And then for the 1 over 4, we are just going to keep that right here. And then what we'll do next is, we'll look at the next 4 terms. And this term right here, we'll change it to 1 over 8. And of course, 1 over 5 is bigger than 1 over 8. So I will just write it down like this. Similarly, 1 over 6 is also bigger than 1 over 8. And then 1 over 7 is also bigger than 1 over 8. And of course, 1 over 8 is the same as 1 over 8. And so on, so on, so on. And the idea is that, you see, this right here is just 1. No problem on that. And I will just put down equal sign because this is how we read this kind of inequality or equations or whatever. From here to here, it's equal. So you see this is 1. So we're going to pay close attention to that. This is 1. And then the 1/2, I will also keep it as 1/2. But 1 over 4 plus 1 over 4 is 1/2. So we'll just merge these two together and then we'll put this down as plus 1/2 right here. And the next thing is that we will see the next 4 terms, 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8. Of course, it's 4 over 8. Of course, that's the same as 1 over 2 as well. And then you can imagine, we will just do the same thing for the next 8 terms because you can see that this is the first term right here. The 1 is just 1 by itself. The first 1/2, and then these two terms is 1/2. These 4 terms is 1/2. And then the next 8 terms is going to be also 1/2 if you change that to 1/16 for the 1/9, all that, right? But anyway, that's pretty much the idea. And then in the end, we will see that this right here is just pretty much 1 plus 1/2 plus 1/2, and then infinitely many 1/2. And of course, this right here, because we are not approaching 0 anymore for the nth term, so we know this right here will diverge to infinity. In another word, you can see that this right here, in fact, it does have an infinite sum. Therefore, this right here diverges. And I'll be using div for diverges right here, okay? And for this one right here, you can call this to be the P series. You can just indicate that we have the little 1 right here. You can just say P is equal to 1. But this is not good enough. You have to say P is less than or equal to 1. And in that case, the P series diverges. I will have a handout of all the convergence tests, like the comparison tests, all that organized for you guys. You guys can also go check that out. But anyway, this is just one way you can say it. Or if you would like to just write down more English words, you can also say the harmonic series diverges, right? So one way or the other. I think I'll just use this way because it's shorter like that. So that's pretty much it. And this is the classic proof, and it deserves to be having a little box and you shade it because we are doing a proof. Okay, that's it. But this is not it for the video. We have 99 more to go, and now I really have to kind of conserve my energy because we really have 99 different questions to go, so this is not a joke. Alright, so I will be erasing the board so you guys can just take a look, and of course, this is going to be fun. Let me know if you guys want to see more of this kind of videos. To be honest, it's actually easier for me to do 100 different questions in a video. It's more organized for me this way, and I can force myself to type out the file so you guys can actually get the file and look over to the questions that you want to work with and all that. Anyway, number 2, we have the natural log of n in the denominator. So here we go. Let me just put this down right here. This is number 2. And for my iPhone view, I'm sorry, I have to focus on the views from the laptop. But anyway, here we go. We are looking at the sum as n goes from 2 to infinity of 1 over natural log of n. Okay, you guys can leave a comment down below and let us know why don't we start with n equals 1 in this case. But anyway, we are looking at this. N goes from 2 to infinity. Now, here is the deal. You really have to remember the list, and I will just put this down right here for you guys. Ln n, it's the smallest infinity, which is less than n to the p's power and all that, right? So this is the first 2 things on the list. Well, let me tell you guys the breaking point. Right here. Look at n to the first power, right? And the thing is that, okay, these are all positive as n goes to infinity. You can take the reciprocal. Another version of the list is that we can look at this as 1 over ln n. In that case, this will be greater than 1 over n to the p's power. And of course, right here, the breaking point is 1 over n. And this is the classic series that diverges. And the deal is that, as you can see, as n goes to infinity, 1 over n goes to 0, but the sum of 1 over n actually diverges because we saw that earlier. And now, as you can see, 1 over ln n, it's actually bigger than 1 over n. So in this case, you can see that this right here diverges as well. And now this is how I will show my students that the 3 steps that we have to write down, namely what we know, and then the check that we have to do, namely to provide the reason, and lastly we have to draw the conclusion. So I will do that, and I will see how many times I will do that until I get impatient maybe, but I'll try my best. Okay, here we go. First thing first, we are going to see that, again, because of the list, we know that I am going to use the sum as 1 over n diverges, and I'll just put down, we know as n goes from 2 to infinity, 1 over n. This right here diverges. And again, let me just put down 1 right here. Again, I would just say P is equal to 1, which is less than or equal to 1. That's the P-series test. This right here diverges. And another thing that we want to talk about before we go is that, notice earlier I started with n equals 1, but this time I put down n equals 2. It's actually okay. You can also put down n goes from 35 to infinity. This right here still diverges. In another word, the starting n value doesn't really matter unless somehow you messed up the denominator. For example, if you put down n is equal to 1, what will happen to the denominator, right? Anyway, this right here is what we know, and as you can see, based on this, we are going to do the check, and then that's pretty much the part that we have to provide the reason. So here is the check. We are going to see that, okay, I want to see, this is the not the improper integral. This right here is the infinite series. In another word, sum as n goes from 2 to infinity of 1 over ln n. Is this bigger than or equal to, put a question mark because I don't know yet, and the sum as n goes from 2 to infinity of 1 over n. You are always going to put down the infinite series that you want to find out on the left-hand side, and always put down the one that you know on the right-hand side. And because this right here is a divergent, and you hope to show that this right here is bigger than or equal to a divergent. Because remember, this divergent is past infinity. Then if you can show this right here is bigger than infinity, what can we conclude? We can conclude that this right here must be a bigger infinity. So of course, this right here has to diverge. So that's pretty much the idea, and it depends on your teacher to see the format of the reasoning that you have to provide on your exam, but I think I'll show you guys this right here to hope make everything clear. Anyway, this is the check that we have to do, and this right here, we are just going to make sure that, okay, everybody is positive, so that's good. And when we have the sum right here, we can just compare the inside. So we are just going to see that if 1 over ln is bigger than or equal to 1 over n. Well, is this true? Yes, this is true. Why? Because of the list. And now I just put down by the list. And if your teacher doesn't let you use the list, then you will have to use L'Hopital's rule, or maybe provide a graph, or maybe do some more calculus to show this is true. But for my class, once you see this right here, if you would like, you can also cross multiply. You can say that n is bigger than or equal to natural log of n for n greater than or equal to 2, right? Because we have n goes from 2 to infinity. So you can also quote the list from here if you would like, up to you. But anyway, this right here is true by the list, right? So it depends on your teacher, I would say. So this right here is true. When we are doing comparison, and if we end up with a true statement, that means we can move on and we can draw our conclusion. So let me just write this down right here for you guys. So my students, remember we have to do 3 parts. What we know, and then do the check, and then write the conclusion. The conclusion is that the sum as n goes from 2 to infinity, 1 over natural log of n. This right here, I will tell you, it also diverges. Because right here, this was divergent, and this is bigger than a divergent. That means the one that we're trying to find out, which is this, is also a divergent series. This also diverges by direct comparison test, DCT. And the direct comparison test is just that we are using inequality to make the comparison. There's also the limit comparison test, and we have to do limits for that. But since we didn't do limit, so we are not going to say that it's the direct comparison test. And up to you, because you show all the work already, you can also be more, complete, I would say, by the direct comparison test with the divergent sum as n goes from 2 to infinity, 1 over n, like this. So with that, we are done. That's question number 2. Okay, now, I'll scare you guys a little bit. We are going to be doing the sum as n goes from 2 to infinity of natural log of n to the nth power. Oh man, let's see what will happen right here, number 3, right? So here we have the sum as n goes from 2 to infinity, 1 over natural log of n to the nth power. And here's the funny part, and let me just write this down right here for you guys first. 1 over natural log of n to the nth power. Remember, ln n, it's the smallest infinity, and then n to the n is the biggest infinity. But the problem is that what if we put ln n inside of the natural log, right? What will happen? And that's exactly what we are going to do right here. Let's see. You can try to use direct comparison test, let me know, but I feel like doing some integral. So I'll show you guys how to approach this with the integral test. And it's not easy to integrate something with like x to the x power whatsoever, but in this case it's actually not that bad because we can take this n to the front. So in another word, this is the same as saying the sum as n goes in from 2 to infinity, 1 over n in the front times natural log of n. And this is very good. Why? Because we can actually do the following. I will tell you, we are going to consider the function, namely f of x, and I will just kind of put all the n into x. So we get 1 over x times ln x, like this. You're going to consider this function, and in order for us to use the integral test, we have to indicate that this function, we have to check that this function is actually positive and decreasing on the interval from 2 to infinity. And it depends on your teacher, I will say. Seriously, a lot of things depends on what your teacher wants you to achieve. For my students, you guys can just show a graph, and usually when you show a graph, you can clearly see that the graph actually, it's like diverges. I mean, not diverges. The graph is like positive and then decreasing like this. I told you get the answer. Well, however, just show a graph right here and indicate that this right here is positive and decreasing, right? Decreasing. So just like this. POS stands for positive, and DEC stands for not December but decreasing. Right? So this is what we are going to do. We will use the integral test, and this is the check that we have to work out. We check the corresponding integral, and it's an improper integral going from 2 to infinity of 1 over x ln x dx. And the idea is that if this improper integral converges, then this will also converge. But if this diverges, this will also diverges. They have the same conclusion in terms of the convergence or divergence. But if you do end up with a nice value right here, this right here, it may be not end up with the same nice value, but it converges as well. Anyway, to integrate this, we'll just use the u sub, let u equal to natural log of x, and then we'll differentiate both sides. Du is equal to 1 over x dx. And if you would like, just get the dx by itself. So dx is equal to, let's multiply x on both sides. So we have x du. And now, as you can see, this is going to be the integral. And when x is 2, remember this is x equal to 2. Put 2 into x, we get u equal natural log of 2. And if we put infinity into x, we will see that u goes to infinity. So in this case, we get 1 over, well, let me put down the x, and then the ln x is u, and then dx is x du. So I just put down x du here. And of course, we can see that the x and x cancel. And of course, we can just do the integral right here. And by the way, the reality is you may not have done integral for a while, so that's why I'm showing you guys all the work, just like review, right? Anyway, by now you guys should hopefully be a integral master. If not, go check out my 100 integral video. Anyway, integrating 1 over u in the u world, we get ln u, and you don't need the absolute value because we'll be going from positive ln 2 to positive infinity. So as you can see, this right here are in terms of u. We'll finish that. Put the infinity, we get ln of infinity minus ln of ln 2. Well, this right here is just ln of ln 2. This right here is infinity. Infinity minus a finite number. This right here will give you infinity. In another word, this improper integral diverges. And if this diverges, we can go back to here and say this also diverges. So here is my conclusion. Conclusion, the sum as n goes from 2 to infinity of 1 over natural log of n to the nth power So as you guys can see, this right here may look really scary, but it's actually not. This right here also diverges by the integral test. I will just write IT for this, right? Integral test by it. Anyway, that's pretty much it. And now let's see, we have that's number 3. So moving on to number 4. This right here, it's also just as crazy. We have natural log of n raised to the natural log of n power. And the reason is just that I want to do some crazy ones first, so that you guys will see, oh, you'll take this seriously. Anyway, here we go. Number 3 right here. We are looking at no, not number 3, number 4. I hope not to make the same mistake as what I did back in the 100 integral video. Anyway, the sum as n goes from 1619 to infinity, right? 1619 to infinity. 1 over natural log of n raised to the natural log of n's power like that. Oh my god. Yes, earlier I put n to the n's power in the natural log. This time we have natural log of n for the base and then natural log of n for the power. This is not funny anymore, but it's okay. It's actually doable. I wouldn't say it's not that bad. But check this out, right? It might be kind of hard to do a comparison right away. We have to kind of just change things into a form that we like. And keep in mind, we like to have the P series or the geometric series to do comparison with because they are the easy ones. So maybe I want to use n to some power to show if this converges or not. Notice earlier, n to the n instead of the natural log, it diverges. This time, the base, check this out, the base is going to be infinity as n goes to infinity. Likewise, the power is also going to be infinity. So this has a good chance to become infinity. I mean, this right here has a good chance to be a convergent, right? Earlier, it was a natural law of infinity, so I don't know. But here is the deal. We are going to somehow change the base to just n, and this is how we are going to make this happen. First of all, let me just do this right here for you guys. I'll put down this in blue. Okay, here we go. Notice, when we have natural log of n for the base, and then if we take this raised to the natural log of n like that, well, let's see. Yeah. Okay, here we go. We don't like to work with base n. I forgot. How can I forget about this? I was saying this 100 times on the other night. Anyway, we don't like to have base being Ln. We like to have base e, usually. If we don't know what to do, just have base e. So this is how we can take care of this. When we have natural log of n, we can write this as e to the natural log of n, like this. Why? Because e and this natural log cancel, and we'll still end up with this natural log. So the blue part is still the blue part. But we still have to take this raised to the natural log of n's power. And now, as we can see, this is a power, that's also a power, so we can multiply the powers. And let me just put this down right here for you guys. We can write this down as e raised to the natural log of n, which is this right here, and then times natural log of n, like that. And what we can do is, we can pretty much kind of do this like backwards. You'll see. We can actually write this as the following. Well, I can actually have the e to the natural log of n first. So I will put this down together, e to the natural log of n, and then I will raise this to the natural log of n's power like that. And the beauty of doing all this is that e to the natural log of n cancel, we just get just n right here for the base. So in the end, we get n for the base raised to the natural log of n like that. Whew, that took some time. So what we're trying to do, what we're saying is that this right here, it's pretty scary, but it's actually just the same as the sum as n goes from 1619 not raised to the infinity's power. From 1619 to the infinities, not the power, seriously. from 16, 19 to infinity, and the bottom is just what we did right here. In another word, n to the natural log of n's power. And now, as you can see, we can feel better about this because as n goes to infinity, we know this right here will go to infinity. And the funny part is that we know 1 over n squared, the series for that, it actually converges. So we are just going to write this down now because again, we're using the fact. And as I said earlier, this had a really good chance of being a convergent, right? So keep that in mind. All right, so here we go. We are going to write down what we know. And I will just put down the sum as n goes from 16, 19. And you guys will know why I start with 16, 19. Anyway, 1 over n squared. And in this case, that indicates that p is 2, which is bigger than 1. This is how you have to write down. You cannot just put down p is equal to 2. Because p is equal to 2, well, doesn't really mean anything. You have to compare 2 with 1 in the p-test. Because later on, once we get into the ratio test and all that, you have to know how to utilize the numbers that we get. Anyway, p is greater than 1 in our case. Therefore, this series converges. And now we just have to do our check. And this is just how we play around inequality. You will see that the sum as n goes from 16, 19 to infinity's power. Not to infinity's power, seriously. All right, 16, 19 to infinity. And we'll write that down, if you would like, 1 over ln n raised to the ln n's power. In this case, we want to show that this right here is less than or equal to a convergent. Because a convergent, remember, this right here is finite. If you can show a number that's less than a finite number, and this is also positive, that will imply this right here also has to be finite. In another word, convergent. So less than or equal to that. So the sum as n goes from 16, 19 to infinity of 1 over n squared, like this. And again, we should also indicate that this right here, they're both greater than 0. So that's good. And the reason we want to include that is because, remember, okay, if you have 5, for example, less than or equal to something, well, this can be negative infinity, right? So it might still be divergent. But the moment you indicate that this right here has to be greater than 0, then we know this right here has to be finite. So that's why we include that. And I'm just taking my time to explain more details during the first couple questions, and later on we'll speed out the process, right? All right, so this right here, it's a setup, and now here's the check. Of course, we have the same summation, so we just compute the inside. That's nice. So we will have 1 over. This right here, of course, is just that. So I'll just put this down in blue, which is n raised to the natural log of n's power, right? So we did the work right here already. Do we get this to be less than or equal to 1 over n squared? Well, I only care about this when n is greater than or equal to 16, 19. Is this true? Well, you can cross multiply because everybody is positive. So in another word, we are looking at this as n squared is this. Less than or equal to n to the ln of ln n power. Well, the base are the same, and these are just positive things. So we can just compare the exponents. In this case, we will just say, well, is 2 less than or equal to ln of ln n? And again, right here, we're in real world, right? And then the base are positive and all that, so there's no trick at all. So we just compare this and that. So this is okay. So we'll just compare this. Is this true? For n is greater than or equal to 16, 19. And the deal is, it is true. If you take e to the both sides, e squared, is this less than just inside natural log of n? Is this true? If you don't know, you can just still do e to the second power like that. Well, this in fact is true. Because this right here is actually about 16, 18. It's almost like 1,000 times of the golden ratio. That's why I start with this. But anyway, the truth is that the starting doesn't matter. If you would like, you could actually have started with n equals 2. That will still be legitimate, even though the inequality is not true when n is 2, 3, 4, 5, and so on. But the main point of the direct comparison test is that we just want this inequality to be eventually true. When n is bigger than certain number, any n value after a certain number, as long as this inequality is true, you can actually say that this is actually good. But for my Cal2 class, usually I'll just try to make things not so weird. That's why I would like to have n greater than or equal to 1619 right here for you guys. And if you use n is, if you use the 1 over n to the third power, that will be confusing. So maybe, on my exam or so, I will give you guys a hint like this. I use this to make a comparison and just have to work this kind of things out. And this is also the hard part that you have to know how to do. All right? So that's pretty much the idea. So this right here is actually true because, as I said, this is approximately 16, 18, and point something. And then just work this out on your calculator. So I will just draw the conclusion right here for you guys. So I will put this down, right? So again, write down what you know and then do the check. And in the end, we will draw our conclusion. So the conclusion is that we have to go back to there. The sum as n goes from 16, 19 to the infinity right here. Not the infinity power, seriously. ln n raised to the ln's power. This right here, I will tell you, this also, what? Also converges, right? By, again, we did the inequality, so it is the direct comparison test. And if you would like, you can just say with the sum as n goes from 16, 19 to infinity right here, 1 over n squared, like that. And with that, we are done, right? So that's not that bad. Oh, no, let's look at number 5. You have the negative 1 to the nth power and all that. All right, take a look. Okay. You can pause the video, right, if I erase too fast. Or go back to the video and keep watching. All right, so I know this is going to take me so much time because I do have to provide so much more explanation rather than just doing the computation. So I don't know how long this will take. Anyway, number 5. Let me just put on right here. Number 5. Well, in this case here, we have the sum as n goes from 1 to infinity. And I personally don't like to write the summation. I like to write the integral signs more than the summation, of course. Anyway, we have the arctangent in the denominator. So arctangent of n like this. This is the arctangent. So does this converge or diverge? Well, nothing tricky at all. The truth is, as n goes to infinity, inverse tangent of infinity, right here, it's actually just pi over 2 in the denominator. So the truth is, this right here doesn't even approach 0. So I will just tell you guys that this right here diverge. Because I'll just write this down. This right here diverge. Because if you take the limit as n goes to infinity of the sequence formula, of the formula right here, the an, right? Of this, negative 1 to the n plus 1 power over the inverse tangent of n. Well, in this case here, if you put infinity right here, you will end up with this. And this is kind of weird. You have like negative 1 to the infinity plus 1 power over the inverse tangent of infinity. And again, on the top, it's actually really weird, but this right here, it's actually the following, right? So infinity plus 1 like this. Over this right here is pi over 2. Now, here's the deal. When we have negative 1 to like whatever, like infinity, in fact, this top does not converge at all, even though the bottom is a finite number, right? This top does not converge at all, but the bottom is a finite number. So the whole thing right here is that this right here does not exist, right? Unless the bottom was infinity, then in that case, the top is like negative 1, infinity, which is like between negative 1 and 1. But when you divide it by infinity, that will still approach 0. In this case, though, because the bottom is not infinity, so it's not powerful enough to kill that part. This right here is technically does not exist. It jumps up and down between this value, like the negative and positive version of that. Well, the truth is, this right here, the limit, so I'll just say diverge right here, since the limit of n goes to infinity of the thing right here, the inverse tangent of n, this right here does not equal to 0. right? And this is called the test for divergence, TFD, right? And I realized I could have just put this down right here, but it's okay. Divergence show the limit does not approach 0 of the term right here. The terms does not approach 0, and of course in that case it diverges. So that's it, right? That's one of the easy ones. Now I am actually going to, right, number 6 right here. Right, number 6. We are going to do this, right? So here we have the sum as n goes from 1 to infinity, and we have 2 to the n over 3 to the n plus n to the third power right here. Does this converge or diverge? Well, this is the point that the list comes into play as well. We have to pick up the dominating part. As you can see, we have 2 to the n, that's an exponential on the top, and in fact that's the only term, right? And on the bottom we have 3 to the n, and the other part is n to the third power. In that case, 3 to the n wins. So this is actually what we have to do. So let me pick up the part. Let me pick up something that we know, and that's actually much easier. Let me just write down as n goes from 1 to infinity. Let's just look at this and that. And as we can see, we have 2 to the n over 3 to the n like this. Well, as you can see, both of them are of to the nth power, so we can write this down as the sum as n goes from 1 to infinity, parentheses 2 over 3 to the nth power. In that case, notice that this right here is a nice geometric series, namely our best friend. So in that case, this is how you have to indicate. You have to indicate the common ratio, which is just inside, that's 2 over 3. And in this case, you are comparing this with 1. The common ratio is less than 1. And technically, you have to say the absolute value of the common ratio is less than 1. So like that. Therefore, this right here converges. Right, this right here converges. So that's what we know. And now let's do the check. The check is, again, we'll put down the one that we're trying to find out. N goes from 1 to infinity of 2 to the n over 3 to the n plus n to the third power. If you know a convergent, then that means you're trying to see this right here. Hopefully, this is less than or equal to the convergent that we already know. So this is the idea right here. 2 to the n over 3 to the n, like that. And of course, I will show you guys the quick way to do it so we can kind of transit to the quick way along the way, all right? But this is how I will tell my students. Anyway, this right here, again, you can just kind of look at this. Everybody is positive, so we can just say both of them are positive. So put down the 0 right here, and then a less than equal to symbol, because we're reading this way. And right here, of course, we will just compare the inside, so we can just put this down. Is 2 to the n over 3 to the n plus n to the third power less than or equal to 2 to the n over 3 to the nth power right here. Well, in that case, again, don't forget to spell 4 wrong. We have to indicate that this right here is for n is greater than or equal to 1, right? Because n goes from 1 to infinity. And of course, you can cross multiply, but the truth is, when we are adding something in the denominator right here, the denominator is bigger, right? If the denominator is bigger while the numerators are the same, that means this right here is actually smaller. And let me just do the usual thing for you guys first. If you would like to just work things out, you can just cross multiply, or you can actually cancel things out. It's up to you. So first of all, you can cancel this 2 out if you would like. Actually, let's just cross multiply just to avoid confusion. So here we have 2 to the n times 3 to the n, this times that, and we will still maintain less than or equal to, because everybody is positive, so you don't change the inequality symbol. And then here we have 2 to the n times this, namely 3 to the n plus n to the third power, like that. And now check this out. This is always positive, so we can cancel them out on both sides. And of course, we have 3 to the n. Is that less than or equal to 3 to the n plus n to the third power? Well, yes, of course it is, right? Because of course they're the same, and then you add n to the third power on both sides. So of course, in this case, you just subtract them on both sides. So you get 0 is less than or equal to n to the third power. And of course, this is true for n is greater than or equal to 1. So you just have to do enough algebra to convince people and convince yourself that this is actually true. But again, you could see that later on, the quicker way to do all this. But anyway, what you know, and then you do the check, and this is true, so we can move on and draw our conclusion. And the conclusion is that the sum as n goes from 1 to infinity of 2 to the nth power over 3 to the nth power plus n to the third power, this right here, also converges by the direct comparison test. Dot, dot, up to you. Dot, dot, dot. But yeah, with the sum as n goes from 1 to infinity of 2 to the n over 3 to the n, like that. And this is the geometry series. I find this to be really helpful if this is the first time that you are doing the comparison test. Right? This is the format that I will show my students. This is just like writing an essay. Your introduction, and then your body paragraph, and you draw your conclusion. But of course, in our cases, put down what you know, and then do the check, just like the body paragraph. You have to do all the work, and then in the end, draw the conclusion, like that. All right? So that's it. But now, let me just tell you guys, this is how else you can do it. Again, look at the series. Well, as you can see, this is plus n to the third power, right? In that case, if you just ignore that, which you are making the denominator smaller and the whole thing is going to be bigger, in another word, notice this right here is less than or equal to, and technically it's always less than, but just put on less than or equal to. I think that's what people like more. I don't know. Anyway, write down the same sum as n goes from 1 to infinity, and you just write down 2 to the nth power over 3 to the nth power, and then you do this again. So this right here, it's pretty easy to see that once you take out something from the denominator, take out something positive, right? You make the denominator smaller, so you are making the whole thing bigger. You can just say that's the deal. So this converges because this is just the geometric series, 1 to infinity, and this is 2 over 3 to the nth power. And again, you indicate that r is 2/3, which is less than 1, absolute value. So converges. And when you have a convergent right here, and this is also less than the convergent, you can say this also converges. So that's another way to write it. And later on, we'll be doing this because if I just put this down, I think it will take me 10 hours to do all this work. So yeah. Anyway, number 7. My God, it's very similar, but it's not quite. We will see. So number 7 and number 6 are very similar, and you have to be really careful right here as well. So here we go. Number 7. Put down this right here. We are going to do the sum as n goes from 1 to infinity, and we have 3 to the nth power on the top over 2 to the nth power plus n to the second power, like that. Now, here is the deal. If you want to just do that, if you just cover on the denominator, yes, this is less than or equal to the sum as n goes from 1 to infinity of 3 to the nth power over 2 to the nth power. But in this case, this right here, it's a geometry series with a common ratio 3 over 2, which right here diverges because again r is 3 over 2, which is bigger than 1. This diverges. But in that case, we cannot draw any conclusion because remember, this is like passing infinity. Well, this might be just a smaller version of that passing infinity. It might still diverge, right? Or maybe it's a finite value. So in this case, we don't know. We cannot do this. The direct comparison doesn't really work, right? If you just do exactly what we did right here, it's not going to help us out drawing the conclusion. The truth is, if you just ignore the n square, we get the sum of 3 to the n over 2 to the n, and that diverges because, like this, direct comparison with the inequality, it's not helpful, right? Because as you see right here already, in that case, let's try the limit comparison test. And I will do the limit comparison test with the 3 steps again. So let's see. All right, here we go. First of all, let's put down what we know. And we are just going to pick up this and that right here. And then we'll see n is 1 to infinity, 3 to the n over 2 to the n. Of course, this is the sum as n goes from 1 to infinity. And this is 3 over 2 to the nth power. And right here, we'll indicate that this is r equals 3 over 2, which is bigger than 1. This right here, it's a divergent geometric series. Well, this is what we know. And now let's do the check. Again, the inequality is not going to work out nicely. So, limit comparison test. I will do the following. We will just do this, okay? You can just say something like, you have two choices. You can put down as n goes to infinity, and then just do the rest of the math without the LIM. I know whenever we take limit, we put on LIM a lot, but like in sequence series, sometimes if you just write this, that's also legitimate, right? So you have to put this down before you can actually do all the work. All right, enough talking. To do the limit comparison test, put down the one that you want to draw conclusion on the top. So in this case, it's 3 to the n over 2 to the n plus n squared. And then we are going to divide this by the one that we know much better, which is that version. I'll just put that down, 3 to the n over 2 to the n, like that. And then right here, we'll just, you see, when you do this, you don't have to write down the LIM like a lot of times. So we'll do that later on. Okay, so you take this and do the reciprocal. So in the end, we get this right here, which is 3 to the n over 2 to the n plus n squared. And we multiply this by 2 to the n on the top, and then the bottom is with 3 to the n. Of course, let's put this down with a parentheses. And notice that we're just doing algebra, so we put on the equal sign right here. And now, let's see. Depends on what your teacher wants you to do. Seriously, right? But let's just do more algebra right here. If you multiply this, you can multiply the base, and the power is still n. So here we get 6n over, if you distribute this and that, we get 6 to the n as well. And then we will have this times that, which is just plus n squared 3 to the nth power, like that. And now, depends on how your teacher wants you to take the limit. I will show you guys the legitimate way first. The legitimate way is divide everybody by the dominating part. The dominating part is 6 to the nth power, right? Because as I said, you have to know the list really well. I will divide this by 6 to the n, divide this by 6 to the n, divide this by 6 to the n. And this is still algebra, so we will still put down this is equal to, on the top we have 1 over, this right here is 1, right? And this right here is plus. And here we have n squared over, 3 to the n over, this is like 3 to the n, 2 to the n. So of course, you can just divide, you get 2 to the n right here, like this. And now, here is the deal. This part, we can draw conclusion from the list. N squared over 2 to the n. As n goes to infinity, this right here is so much bigger than that. In another word, this right here goes to 0, right? Because n to the p is so small compared to 2 to the n, like b to the n, when the base is bigger than 1. So this goes to 0. In another word, this right here goes to, and now I'm drawing arrow because from this step we are taking a limit, just 1 over 1, which is just 1, like that, right? So this is a more legitimate way to take the limit. A not so legitimate way to take the limit is that you just circle the biggest part and circle the biggest part, and you just totally ignore that part. And in another word, you have 6 to the n over 6 to the n is still 1. So it depends on your teacher. For my students, that's okay. But anyway, this right here, when we do the limit, this is 1. And it's 1 and useful in our situation. Yes, it is. When we are doing the limit comparison test, this 1 is useful, and we have to compare this with 0. So this is actually good. If we do the limit comparison test, and if we end up with 0 or infinity, we have to be super careful. Sometimes your teacher might not go over those situation, and in that case, we just don't use that. It's still doable. It depends on the situation. But as long as this is a finite number that's bigger than 0, this is useful. This is like saying, you see, the ratio of this and that are about the same, because when you do this divided by that, as n goes to infinity, we have 1. So this and that are about the same. Earlier, this one, the one that we know, diverges. In other words, this right here, it's almost the same. Diverges as well. So we can actually draw conclusion. I just need to find a place to write that down right here for you guys. So I will put this down. Conclusion. All right, the one that we are trying to do is the sum as n goes from 1 to infinity, 3 to the n over 2 to the n plus n squared. This right here also diverges by the limit comparison test with that. And I'm just going to skip that so I can have more time, right? So these two questions are similar, but like the number 6 is direct comparison test, and the other one is the limit comparison test. Oh my god, 7 questions took me like almost an hour. That's, oh my god. All right, so we have to kind of just see these kind of things. And hopefully, you guys are like paying attention to the first maybe 10 questions, so that way you guys can really get the idea of like what's going on with all the approaches and all that. And then later on, I'll show you guys like a slightly quicker way to write down your reasoning once we get more comfortable with all the things. All right, number 8. All right, number 8. We have to take care of the sum as n goes from 1 to infinity. And we will just put on 2 on the paper, but it doesn't really matter. We have to do n to the third power sine square n over n to the third power plus 2, like this. Now, I want to show you guys the quicker way to write down your work. Whenever you do like sine cosine, like they have like weird numbers, right? They keep repeating. When we have sine square n as n goes from 1 to infinity, and notice that in our case here, we are in radians mode. So sine of 1, sine of 2, sine of 3, sine of 4, and all that, sometimes they're positive, sometimes they're negative. However, even though some of them are positive, some of them are negative, some of them are positive, some of them are negative, but you square that, this is always positive, and the rest are always positive as well. And the beauty is that, you know what? I wrote it down wrong. It's meant to be n to the first power right here on my paper, right? Right, anyway, this right here, we're just going to get rid of the sine squared by taking the absolute value. So this is the check that we can do, right? Well, actually, yeah, I would just say notice, right? So whenever we have the sine cosine, let's just take the absolute value and check for the absolute convergence and all that. But since it's positive anyway, so anyway, sine square n right here, and then n to the third power plus 2. Here we are going to take the absolute value. So I should have say we're going to check, because that would be a much better term right here, right? We're going to check for absolute convergence technically. First thing first, this right here is less than or equal to, right? Whenever you have n squared, if you have the absolute value, well, we know sine of anything is less than or equal to 1, right? So that's what we know. So this right here will be just 1. So in other words, we will have the sum as n goes from 1 to infinity. And again, everything is positive, so the absolute value doesn't really matter anymore. But the good thing is that we can replace this with 1, and we have the inequality now. So in other words, we can just put down n times 1 over n to the third power plus 2, like this, right? So that's the deal. And as you can see, we can actually just write down our inequality. And this is like a more master way to just write things down instead of the what you know and do the check and then put on the conclusion. All right, so once you're comfortable with those 3 things, and then you can do it this way. Notice we're adding something positive in the denominator. Let's just ignore that. In that case, we know this right here is going to be smaller than the sum as n goes from 1 to infinity of n over n to the second power, n to the third power. And then, of course, we can simplify this very nicely, right? We get this is equal to, because this and that is actually just equal, the sum as n goes from 1 to infinity, n over n to a third power, reduce that, we get 1 over n squared. And notice that this right here, I'll just circle, this right here is p, which is 2. And in this case, you have to know that p is greater than 1 because we're using the p-test. Therefore, this right here converges. So, you see that this is less than a convergent. In another word, we can also say this right here also converges, right? And I think from now on, I'll just go back to here and I'll just tell you guys, this right here converges by the direct comparison test. And better yet, you can also say it's actually absolute convergence because you take the absolute value of the terms. But because everybody was positive in the first place, so it's not that fun. Anyway, so this right here is it. And I don't need to erase the board. All right, so that's nice. Now, number 9. Okay, we have the sum as n goes from 1 to infinity, and we have negative 1 to the nth power over square root of n plus 1 inside like this. Okay, here's the deal. I will tell you, let's put this right here in the front a little bit, depending on which form you are more comfortable with. If you put the negative 1 to the n in the front like this, and then you have 1 over square root of n plus 1. You can recognize this much easily. This right here is an alternating series because you have the plus minus, right? When n is 1, you start with negative term first, and then the next term is positive, and then so on, so on, so on. Well, alternating series, it requires us to do two things. Take this part to be the Bn. So I will just tell you guys that. Notice, well, actually I'll just say check because when I say check, it sounds like we are doing the work. Two things that we have to check. First, does Bn approach 0? I don't know. Let's take a look. Right here, I will just do 1 over square root of n plus 1. Does it approach 0 as n goes to infinity? Well, yes, it does, because if you put infinity right here, this should be pretty clear, so you can just put a check. So just write that down. And secondly, you will also have to check, is Bn decreasing? In another word, the next term, is it less than or equal to the current term? Well, we are just going to play around with the expression. We will just put the n plus 1 into the n right here. We get 1 over square root of n plus 1 and then plus 1. Does this, do we get this being less than or equal to 1 over square root of n plus 1? Yes, it does, because right here again, the denominator is actually bigger, so that this term is actually smaller than that. And if you would like, you can write this down as a square root of n plus 2. And you can do a lot more algebra. You can multiply things on both sides and all that, but I showed you guys that earlier already, so that should be pretty convincing. So I would also put on 4n is greater than or equal to 1, but that's pretty clear. So now, this right here, I will tell you, it converges by the alternating series test. And again, these two are the things that you have to provide to get full credit on your paper. Okay, this is good. And let me tell you, for every 10 questions, number 10, number 20, and all that, we'll be actually finding the sum. Because so far we just test out if this converges or not, but like 10, 20, and all that. So we will be having 10 questions that we actually have to compute the sum. So that would be great. Now let's see. Number 10. Right. Okay, here we go. Number 10. If possible, we are going to calculate 1/2 minus 1/3 and plus 2 over 9 and minus 4 over 27 and plus dot dot dot. As you can see, this alternates, but don't let that bother you too much. What happens though? Let's see. From 2 to 3, it's kind of hard to see, but if you notice, from 3 to 9, it's just multiply by 3 in the denominator, and then from here to here, again, you multiply by 3 in the denominator, and check this out. On the top, from here to here, from here to here is multiplied by 2. From here to here is also multiplied by 2. So I suspect that this right here is a geometric series. And to just make sure, this is what you can do to get the common ratio. R is equal to, you pick any term that you want. And because this is kind of weird, so I'll just pick the second term right here. So that's negative 1 over 3. You pick any term that you want. Divided by the term before, which is positive 1/2. And if you just do this right here, of course you can put a 2 right here, so you get negative 2 over 3, isn't it? And notice this is the common ratio. When you have 1/2 times negative 2 over 3, the 2 cancel out, so you just end up with negative 1/3. That's very nice, and so on, so on, so on. So this right here actually is the common ratio, right? So you can just kind of double check. And because, notice that if you take the absolute value of the common ratio, this is less than 1. So of course, checks. That means this right here converges. And when we have a geometric series that converges, we actually can use our best friend to help us out with that, right? So here we go. I will just write this down right here to save some space. This is what you can do. This right here, let me just tell you, it's always going to be the first term, which is 1/2, right? It's the first term over 1 minus the common ratio. And the common ratio, don't forget, you still have to pick this one. It's actually a negative 2/3. So you minus negative 2/3 like this. And then you just have to do the algebra and all that. So this right here is just 1/2 over, oh my god, fractions. Okay, this is 1 plus 2/3, which is 5/3. Yeah, and then 5/3. And then if you just do that, so 3 on the top, 3 over 10. Yeah, 3 on the top, and then 5 and 2 together, so you have 3 over 10. And then we are done. Okay, it's a lot of fun. Now, number 11. Here we have the sum as n goes from 1 to infinity, parentheses 1 over square root of n minus 1 over n, like this. Right? Hopefully you guys are following along as well, even though this is like 1 hour and 7 minutes. But we are still strong, right? First thing first, this right here is not a telescoping series because this and that, they are not of the same kind. Here we have the square root of n. This is just the n by itself. Take a guess. Does it converge or diverge? Well, first of all, if you take the limit, it may be kind of hard to see that, huh? But I will let you just show you guys this though. If you have the sum of 1 over square root of n, that one actually diverges. If you take the sum of negative 1 over n, this right here also diverges. So in another word, this is almost like a divergent minus divergent, and while we're trying to, like, are we going to get divergent as well? We don't know unless we do more work. But you have a few ways to do it. Perhaps the easiest way is you can combine the fractions and all that. So I will just show you. Okay, I'll just tell you guys a few things that you can do. You can combine the fractions and then you can do direct comparison test. You can do direct comparison test with 1 over square root of n. Sorry, maybe limit comparison test. Limit comparison test, right? So I will leave that to you because the truth is this right here does not go to 0 in the first place. So I will just tell you guys this right here. So we'll just do the limit check, right? Test for divergence check. And for this one, okay, for the limit comparison test, I don't know. I'll still just write down as n goes to infinity, all right? Right here, 1 over square root of n minus 1 over n. In fact, this right here goes to infinity. Why? Because this is actually a much bigger infinity than that. Well, depends if you believe it or not. If you want to do more math, then you will have to just combine the fractions. I think I will still combine the fractions. N square root of n, put the n over there, minus square root of n like this. Hold on. Oh, I take it back. I take it back. This right here actually still go to infinity. Still go to 0, right? Let's see. Oh yeah, unfortunately this right here actually still go to 0. Sorry, the test for divergence does not work. Unless I'm making mistake. I don't know. I was actually like preparing this like the whole day yesterday, so yeah, I'm tired already. So hopefully you guys can excuse me on that. Anyway, we'll just do the following. Of course, let's just combine the fractions inside. So this is the sum. Just kind of, I'm going to put the timestamp right here, so you guys won't see that. So this is 110. Okay. Anyway, as n goes from 1 to infinity, let's just combine the fractions. Of course, we can just get a common denominator, which is just n times that, n times the square root of n. And then right here, I need the n right here. And then right here, I need the square root of n. So this is what we are having. And now, can we do some tests for, well, the test for divergence doesn't work. This right here actually goes to 0. And we'll just do some comparison. And I will actually just do this for you guys. This is actually what we know much better. So let me put down what we know right here. Right? So I'm going to use the limit comparison test. Right? Usually limit comparison test, I like it more. So anyway, we are going to put down the sum as n goes from 1 to infinity. And on the top, the dominating part is just the n. On the bottom, the dominating part is that. So I will just put down n over n square root of n like this. And of course, you can see that the n will cancel, so we just get sum as n goes from 1 to infinity, and this is 1 over n to the 1/2 power. And because here the p is 1/2, which is less than or equal to 1. In other words, this right here diverges. So I hope to show you guys that this right here also diverges, and to do that, I will just check the limit. And to do so, I will just put down as n goes to infinity. I will put this one on the top, so we get n minus square root of n over n square root of n over the one that we know much better, which is 1 over square root of n, because everybody is having square root of n, so let me just put that down. Now, let's do some algebra. This right here, you put this like that, so we have n minus square root of n over n square root of n, and we just times square root of n over 1. And of course, you can see that this and that will cancel. Well, you can just reduce this and just do the algebra here. The first time you get 1, right? The first time you get 1, and then next time it's minus square root of n over n, which is 1 over square root of n, right? Because remember, this is like saying square root of n times square root of n. So if you divide, you get that. And as n goes to infinity, as you can see, you get like this, 1 minus 1 over square root of infinity. Of course, this right here becomes, goes to 0, goes to 0. So in the end, this right here approach 1. Does the 1 help us? Yes, it does. And you have to indicate that this right here is bigger than 0. Bigger than doesn't have to, you cannot have the equal sign. It has to be bigger than 0 when we're doing the limit comparison test. So this right here, I will just draw the conclusion here, right? I'm not going to write down the conclusion anymore because it's too many words. Anyway, this right here also diverges. This also diverges by the limit comparison test. All right? I think I'll just keep this format because I have so many more to go. So hopefully you guys can excuse me. I'm not doing the 3 steps. So conclusion is this. All right, so that's the deal, right? Okay, so I'm going to drink some coffee to make my mind. All right, now next one, we have this. So number 12, right here, we have the sum as n goes from 2 to infinity. And let me just put on 2. I don't know why sometimes I have that 2 or 3 on my paper. 1 over n squared ln n like this. Well, does it converge or does it diverge? If you look at this part, the sum of 1 over n squared, that converges. That's nice. If you look at that part, 1 over ln n, that diverges. But you see that on the bottom, oh, I cannot put down. It was meant to be a 3. Okay, I'm sorry. It was meant to be a 3. To make things slightly easier, right? So anyway, number 12 right here. The sum as n goes from 3 to infinity of 1 over n squared ln n. Does it converge or does it diverge? Well, here's the deal. I really don't know, but however, 2 or 3 up to you guys. Anyway,不要了，我不要了。